All right, so a couple days ago we finished up talking about physical properties. We said that there are things that can be measured or observed without changing matter into a new type of matter. And in fact, yesterday in lab we worked on some of these measurements. We measured volume, mass, and density. We didn't measure density directly, we measured density indirectly, right? And what are the units for density? What do you think? Yeah, exactly. So it's mass over volume, right? So it's always going to be your unit of mass, which in this case will be grams, over volume, which is either milliliters, which is what you did in lab, or centimeters cubed. Usually chemists use milliliters, though, for volume. All right, today we're going to switch gears and talk about chemical properties, which are a little bit different. So let's first define chemical properties. Chemical properties describe how matter reacts. With other types of matter. So everything's made of matter. We know sometimes when matter interacts, you get something new out of it. The key thing with chemical properties is we really are looking for a change, right? So let's make a note of that. So it cannot be observed without a chemical change. So change is kind of the key feature of this one. Physical properties we can measure without changing things. Chemical properties are normally the result of some sort of observed change. All right, and the key takeaway for this one is it changes matter into a new type of matter. Yep.
And you learn it.
Mm-hmm.
It changes to powder, but there's not. That's more physical.
So we'll talk about that. So the question was, if you have magnesium, has anybody ever seen magnesium? Magnesium is just kind of this gray metal. You can actually light it and it burns like a sparkler. And then at the end, you're left with this powdery residue. That powdery residue is actually a new type of matter called magnesium oxide. So it's not regular magnesium, it's now a combination of magnesium and oxygen. Do you think that would be a physical change or a chemical change? Chemical change, because we're actually changing the type of matter from pure magnesium to a combo of magnesium and oxygen. So sometimes it can be a little bit tricky to tell the difference between those. But what I mean by new type of matter is new compound or molecule. Oops, if I could spell compound. And we'll talk more about what a compound or a molecule is, but the most generic term for a compound is it's a mishmash of two different elements or more than two different elements combined together, right? So we'll take a look at a handful of examples, some that most of us should be familiar with, especially living in the Northwest. If we have iron, which is found in steel, and you expose it to oxygen for a long period of time, what do you get out? Rust, exactly. So rust is actually called iron oxide in chemistry, and it's a combination of that iron reacting with oxygen in space. It's one reason why oftentimes cars actually have coating over their steel is to prevent any sort of corrosion, right? In fact, on spacecraft, it's a really, really big deal. If you ever look at satellites, what do you notice that satellites are wrapped in? Gold. So sometimes they actually have this really thin gold leaf around them to prevent corrosion. Gold is pretty unique. Gold won't react with oxygen. That's why it's called a precious metal, is it's one of the few metals that won't react with oxygen. It's kind of neat. All right, the next one.
So if anything reacts with oxygen, then it's a chemical change?
Yeah, if anything reacts with oxygen, it could be considered a chemical change. Exactly. Yep. So let's take another one. So let's say we react wood with oxygen. And we have some sort of heat source. What do we get out? Does anybody know the chemicals that will be spit out of this reaction? What do you think? CO2. So carbon dioxide is the byproduct of burning things typically. Sometimes you get a little bit of carbon monoxide too, but mostly it's CO2. And then in addition to that, a lot of people don't know, but you were entirely right. It also spits out water as well. So you get CO2, water, and then typically you have stuff that can't burn. We just call that ash. That's typically just leftover carbon material that didn't combust. So most of us are familiar with burning things. So both of these would be considered chemical reactions. Yeah?
So essentially in any case, if you burn something, it would be a chemical reaction?
Yeah, anytime you burn something, it would be considered a chemical reaction because we're changing it from one molecule or one type of compound to another type of compound. And then the last one is one that always drives me nuts when I visit my family. So my grandmother has this heirloom silver that she insists on busting out for every single holiday, and she counts it before and after to make sure she doesn't lose anything. And then at the end, she makes me sit there with this cloth and polish them. Does anybody know why? So silver forms something similar to rust. It's called tarnish. So you get this kind of blue-gray luster on the outside. It makes it a lot less pretty, and so you have to sit there and clean off that tarnish. It's one reason that gold is worth a heck of a lot more than silver. Is gold, like I said, is inert, where silver will actually react with oxygen. So we do have to clean our silverware. All right, so what I'll do next is I'll give you a list of some situations, and I want you to help me determine whether or not the change is physical or chemical. But before you do that, I want you to check with your neighbor. So we'll make a list here. All right, so the first thing I'm going to do is fry an egg. Next one, we're going to freeze water. Next one, we're going to crush rock. Whoop. Then we're going to digest food. And then we're going to evaporate water. All right, so see if you can figure these out and then check with your neighbor and see if you can agree on whether or not the change is a physical change or a chemical change. All right, so let's check in on this. How many of you felt really confident about this? All right, that's good. I think it's good not to be confident. Otherwise, we're not being challenged, right? All right, so first one, frying an egg. What do you think? So some people are saying physical because you're just adding heat. One thing to think about, though, is whether or not the substance is really changing during this process, right? Is it changing into a new type of compound? So another way of thinking about it is at the beginning you have raw egg, and at the end you have cooked egg. Are they the same? No. Not quite. Another way of thinking about this is, can you ever uncook an egg? No, you can't uncook an egg, right? So because this is a process that's irreversible, we're changing it into a new state of matter. This must be a chemical change. It's a pretty interesting process. If you ever take biology, you'll learn about proteins, right? So proteins are in eggs, and when you apply heat to proteins, they do something called denaturize. Basically, you break apart those proteins, and sometimes they'll cross-link with other proteins. You get a lot of unique chemistry going on. So you're actually changing the state of these proteins in eggs when you cook them. So that is a chemical change because we're making and breaking bonds, which we'll talk about later. All right, next.
Is that safe to say that always, if you can't do it, it's the chemical?
Yeah, we'll take a look at another example here in a second that's a bit more abstract, but hopefully it'll make sense. So let's think about freezing water. Is that a chemical or physical change?
It's
Physical, right? When you freeze water, it's still water. You can reverse it and go back to liquid water. In each case, it's water. Water's not being changed at all. It's just changing the state that it's in. So this would be a physical change. All right, the next one's a little bit trickier. Crushing rock. Physical. All right, but then people will say, but you can't uncrush a rock.
But it's still rock.
It's still rock though, right? So in this case, it would be a physical change. And in many ways, it depends on how strong you are, right? If you're thinking about a planet over millennia can actually take pieces of rock and fuse them together and reform a bigger piece of rock too, right? So it does depend on kind of your perspective. All right, next one, digesting food. Chemical, right? So you're actually breaking a bunch of bonds in food. In those bonds, you have a lot of energy. We need that energy. That's why we eat food. So we're trying to get that energy out of those bonds. This is definitely a chemical change. All right, and then the last one, water evaporating. Physical. All right, so when we think about water evaporating, where does it go? Does it just disappear? No, it becomes humidity in the room, or we can even see it in the sky as clouds, right? Clouds, if they get big enough, will rain and reform liquid water. It's just water changing states, right? So this would be a physical change. So that's the big takeaway from this, is a chemical change. You're changing one type of matter into a new type of matter. It normally involves the rearrangement of atoms or the making and breaking of bonds, where a physical change is just changing the state of something, right? So maybe making it smaller by chopping it up, or maybe freezing it or heating it, but ultimately the material in and of itself is exactly the same, right? All right, so now what we're gonna do is we're gonna try to classify matter in a bit more detail. And I am a big fan of flowcharts, so we're gonna start building a flowchart off of this, but before we do, we're gonna take a step back to 3rd grade and talk about the 3 main types of matter. All right, what are the 3 main types of matter again? Yeah, solid, liquid, and gas. Somebody brought up plasma yesterday. I was pretty impressed with that. We said plasmas are what? Does anybody remember? We had an example we're familiar with. Fire, right? So it's actually a superheated gas is a plasma. We're just going to kind of ignore that because that's something that's kind of unusual. All right, so we've got solids, liquids, and gases. We should all be familiar with those. Solids are easy to remember because they retain their shape. A liquid will flow and fill bottom of container. And then a gas will assume the shape and volume of a container. There are some that are kind of weird. So let's say quicksand. What is quicksand? Is that a solid or a liquid? You can just say yes, right? It behaves kind of like both. So sometimes we run into these states of matter that are kind of in this gray area where they can behave like a solid or a liquid. So if you think about a landslide behaves a lot like a liquid, but it's made up of solid. So there are kind of crossover areas as well. Yep.
What about non-Newtonian fluid?
Yeah, exactly. So a non-Newtonian fluid would be a good example. Has anybody ever played with cornstarch and water and made that oobleck stuff? So that's a good example of a non-Newtonian liquid. So if you set something on there, eventually it'll sink, but if you hit it hard, it behaves like a solid, right? So it is kind of interesting. We often teach students that there's these discrete types of matter. The reality is sometimes it's not always cut and dry like that. All right, so those are the 3 main types, but oftentimes matter gets more complicated. So I'm going to make this flowchart to help us out. So matter is the stuff that makes up everything, right? And matter can fall into two categories. It can either be a pure source of matter, or it could be a mixture, right? All right. And then things even get more complicated from here. So what we'll do is we'll look at pure matter first. And we'll divide this into two categories. The first category of pure matter is elements. So elements are pretty easy to spot. If you look on the wall here, we've got the periodic table of elements, right? So if you look on there, does anybody know what H stands for in that top left-hand corner? Hydrogen. So let's say you have just one atom of hydrogen floating around. That would be considered an element. If we look on the right-hand side on the top corner, we've got helium, right? So helium would be an element. You can get a balloon full of helium, meaning you've got a balloon full of a pure type of matter, right? All right. Next, though, we have compounds and molecules. And these are a little bit different than a pure element. So over here, we said elements are one type of element. And we said that a good example of this would be helium in a balloon, where helium just hangs out by itself. A compound, on the other hand, is more than one type of element. And they are bonded together. And so you can think of bonds right now. We haven't really talked about them in much detail. But if you're bonded to a person, right, meaning you're attached to them in some physical or spiritual way, it's the same idea with these elements, right? They're attracted to each other. They stick to one another. Does anybody know an example molecule or compound? H2O, exactly. So if we think about water, most people, even non-chemists, are familiar with water. And water is represented as H2O in chemistry. And why do you think it's represented as H2O? Yeah.
Two hydrogen and an oxygen.
Yeah, exactly. So we've got that subscript 2 to indicate we've got 2 hydrogens for every 1 oxygen. So it's always in a 2-to-1 ratio of hydrogen to oxygen. So that would be a good example of a molecule, right? And then over here, we've got mixtures. Mixtures get a little bit more complicated. The first type of mixture that we have is homogeneous. And then the second type that we have is heterogeneous. All right, so now we've got to get into our prefixes. Does anybody know what the prefix homo means?
Same.
The same, right? So if we think about this, we know immediately that this must be the same throughout. Whoops. Where this one must be different throughout. All right, so it gets a little bit weird to think about, but we can have a homogeneous mixture. Let's say we put sugar into water, right? If you stir it up, that sugar will eventually dissolve, and then you'll have a pretty uniform mixture of sugar water, right? Where a heterogeneous mixture might be a little bit different. My favorite example of a heterogeneous mixture would be something like pizza. So you're mixing a bunch of food ingredients onto dough, but it's not mixed evenly, right? You might have a pepperoni in one chunk, you might have a pepper in another chunk. It's not evenly mixed at all. Does that make sense? So we've got these 4 classifications of how we can describe matter. We can say it's either a pure element, it's either a pure compound or a molecule, it's either a homogeneous mixture, or it's a heterogeneous mixture. I did want to bring up one super small note, and that is the difference between a compound and a molecule. A compound is defined as two or more elements, specifically different elements, where a molecule can be two or more elements of any type. Meaning those two elements can be the same. So for example, the oxygen we breathe is actually O2, meaning it's two oxygen atoms bonded together. Would that be a compound or a molecule? It would be a molecule. People might look at you funny if you say a compound. However, I don't think you'll really offend anybody if you mix them up. It is important sometimes to know the difference, though. Yep.
Another, back to the heterogeneous mixtures, another example of that would be how you put water and oil together, they can't mix.
Yeah, so if we think about water and oil, they'll form layers. There'll still be one liquid throughout, but they won't be evenly mixed. So I would call water and oil a heterogeneous mixture. That's a great one. All right. So now let's talk about what elements are really briefly. We'll come back and talk about this later. Elements are the fundamental building blocks of matter. So for a long time, we actually scoured the earth trying to figure out what all the different elements were that made up matter. The cool thing today is we actually use these advanced particle accelerators to make new elements, which is pretty crazy. So if you look down at the bottom of the periodic table around 114, 116, you notice those holes? We've actually filled in those holes. The problem is we've made this new type of element. Those elements are super duper radioactive and fall apart like in a fraction of a second. So more it's this novelty that we're able to do it. They're not super practical. All right, so elements are those fundamental building blocks. We've got about 118 elements. Some occur naturally, some are synthetic. All right, let's compare this to a compound or a molecule. Just one more time. So we've got elements over here. Elements, if you remember, are always something that come off of the periodic table. So if we think about the example of helium, the symbol we use for helium is He. So it'd be a bunch of these helium atoms kind of floating around in space, kind of bumping into one another. Versus a compound, like water, we would have a hydrogen atom that's directly bound to an oxygen atom that's directly bound to another hydrogen atom, kind of like that in space. And then over here we might have another water molecule, but they're always, always, always stuck together. So two or more elements stuck together. One important note is if you're not familiar with the periodic table, you'll notice some symbols have just one letter and other ones have two. We have to be really, really careful with capitalization to make sure that we're not mixing things up. So when you are looking at the periodic table, always double check whether or not you're using capitalized or non-capitalized letters. So for example, some people will look at AL, that's number 13, and they think that that's actually two different elements, when in reality, that's one element, right? That's lowercase l, so double check for that. Make sense? Yeah?
Does that red line kind of zigzagging across the periodic table mean anything?
Yeah, so that purple stair step going down on that right-hand side actually shows a transition point in the periodic table. We'll talk more about the periodic table later. those elements that kind of follow the stair step are kind of in between metals and non-metals. We call them metalloids because of that. And so we have that little stair step to indicate that these are kind of unusual elements. All right, good questions. The elements. I don't think Sharon will want you to memorize the periodic table, although I'm not teaching the class. I do remember in grad school, oh man, I had a grad school class where he wouldn't give us the periodic table. In fact, the first page of the exam was you writing out the periodic table, and I was like, what a waste of memory space, man. All right, anyways, that's just me griping. Let's go on to measurement of matter. So, measurement of matter, we've gone over a few times. We said we can measure physical properties pretty easily. The big thing we need to talk about next is the units, and we've talked about this briefly. We said that, for example, with weight, that in the United States we measure things in pounds, but everywhere else measured it in grams. And that has to do with this system that was developed. Scientists like to use units called SI units. This comes from this meeting that they had in France with a bunch of scientists from all over the world. In fact, they just had another big meeting recently where they redefined some of our units to be more accurate. So for a long time, if you wanted to determine whether or not something weighed a true kilogram, you physically had to go to France or one of these other places around the world, and they had a brick that weighed exactly 1 kilogram, and everything else on our planet was standardized to that brick. So scientists got together recently and started trying to define it a bit more clearly because not everybody had access to that brick to calibrate their equipment to. So it's a pretty interesting group. They like to be very particular about things, but they came up with a bunch of units. So we'll make a list of the physical property along with the corresponding SI unit. And then we'll list the SI symbol. All right. So we've got these 3 classes. We'll first list some physical properties. We've got length, we've got mass, we've got volume. A lot of these were what we talked about the other day. We've got temperature. I'm going to put a little space in here. We've got time. We've got current. We've got something called luminous intensity. And last but not least, we've got amount. So these are the main physical properties that we have units for. There's other properties that we measure, like density, but density is really just a combo of some of these, right? So they're just offshoots of these base SI units. All right, does anybody know the standard unit for measuring length or distance? Give you a hint, it's not yards or foot. Meters, right? So the rest of the world uses meters. In fact, if you cross the border and go into Canada, you'll immediately see all of the signs are in kilometers per hour. Kilometers is just a type of meter. Does anybody know how many meters are in a kilometer? 1,000, right? So it's just a larger amount of meters, right? The symbol is pretty easy to remember. It's lowercase m. So 1 meter is about a yard, give or take, right? It's not exact. Those of you that do swimming probably know the difference between a long and a short distance pool. The long distance pool is measured in meters, and it's always disheartening because your times are way worse in those pools. All right, next one, mass. It's not pounds. How did we measure mass yesterday? Grams. It's a little bit weird for this one. The standard SI unit is kilograms. However, I'm going to put an asterisk here because chemists like to just use grams, right? So we'll make a note at the bottom. All right, the standard symbol is lowercase k, so make sure that you do pay attention to capitalization, and then G for grams, right? We don't want a capital K. All right, and then volume is measured in liters. However, most chemists measure volume in what? Milliliters. So again, chemists kind of vary on this. The symbol for liters is capital L. So again, make sure you remember to capitalize or not capitalize certain symbols. Temperature is a kind of tricky one. Does anybody know the SI unit? So Celsius is one. There's also another one. Kelvin. It's a little bit weird. So there's two of them. Kelvin is technically the SI unit. However, chemists typically don't use Kelvin necessarily. Oftentimes we use Celsius. But it's really, really easy to convert between the two. If you know the temperature in Celsius, all you do is add 273, and you'll get a number that is spit out to Kelvin. Does anybody know what 0 degrees Kelvin is? It's absolute zero. So 0 degrees Kelvin essentially means things are so cold that movement stops altogether. It's more this theoretical idea than it is a reality anywhere in the universe. In fact, we've measured the coldest spots in the universe. It gets pretty close to absolute zero, but we've never found a spot that is absolute zero, right? All right, Kelvin is typically measured in capital K. Again, that's why capital K is very important to distinguish from lowercase k. Lowercase k stands for kilo, capital K is for Kelvin. Yep.
So you said that you found places that got close to absolute zero, but not quite. So it's more like absolute zero is kind of something that is observed through data and not through, well, not data, but just kind of putting things together and calculating what could be absolute
Yeah,
zero.
so the absolute zero is more an idea, right? So we've developed the math for this idea that at a certain point, movement will cease altogether. There's actually a cool, does anybody watch Nova on PBS? There's an episode called Absolute Zero or The Science of Cold or something like that. So Americans tried to get the coldest temperature ever, and I think they got within like a trillionth of a degree to absolute zero. And what they observed was atoms slowed down so much that they actually stopped behaving like atoms. And the scientists that studied that won a Nobel Prize from it. They theorized it for a long time. It was called the Bose-Einstein condensate. But really, matter behaves super weird when you get it really, really hot or really, really cold. It stops behaving like the matter we know and love. All right, time is an easier one. How do we measure time? Seconds. Which is easy. The symbol for seconds is just lowercase s. Current is a little bit different. How do we measure current in a home? Think about electricity. Not quite. Amps. And the symbol for that is capital A. So that's the current going through wires at your home. That's different than voltage. Voltage, if you go on and talk about physics, that's a potential energy difference. It's not current. So the way I like to remember it is current can be thought of as like river current, right? So it's the volume of something going through a particular place. Voltage would be like how big of a drop a waterfall has. Even though a waterfall might drop 100 feet, it could have just a little trickle of water, meaning it could have a low current but a high voltage. Same thing, it could have a high voltage, meaning a really big drop in a waterfall, and a really high current. Those two are completely unrelated properties. All right, luminous intensity is related to lamps and things like that. We're not really going to use that, but I thought I would show it. It's candela. And that's abbreviated CD. And then the last one that we're going to spend a fair amount of time with this term is amount. With small amounts, we can just count them with whole numbers. We can go 1, 2, 3, 4. But if you try to do that with elements, you're going to have a bad time, right? Because elements are super duper tiny. You're going to be counting into billions and trillions and even higher. So instead, scientists have this unit called a mole that can be abbreviated MOL. And we'll talk more about that later, but that's an incredibly large amount of atoms, and it just makes it easier for us to use. It's kind of like how bakers use a dozen rather than counting things individually. It's just an easier unit to handle. All right, so I did have 3 asterisks there, one for kilograms, liters, and Kelvin. So I'll make a little note that chemists often use different units. They often use grams, milliliters, and Celsius. So for example, in lab, you'll be working with thermometers. I've never in my life seen a thermometer with Kelvin units on it. It'll be Celsius units, but we know how to convert the two. All right. So the next thing kind of goes off of that last idea we went over about moles, that chemists often deal with incredibly large or incredibly small numbers. So we have to be very careful with how we deal with them. So scientists often use prefixes. And they measure something very large or small things. All right, so I've got a good example for you. I think this is the mass of Earth. So this experiment was done a while ago. It's pretty impressive. I think they did it in the 1700s. They were able to determine the mass of our planet. And it's going to take me a while to write this out. But it's 5,970. And let's see, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 grams. That's a very, very big number, right? So if we're trying to measure the mass of something like a planet, that's going to be an extraordinarily large number. That's a good question. What would we call that? I don't even know what the prefix would be for that. But what we can do is we can imagine that there's a decimal point right here, right? So the decimal point would just be at the end of that number. And what I'm going to do is I'm going to take this decimal point and I'm going to swing this decimal point all the way over here. So we're going to move to the position right after the first non-zero number. All right, so now the question is, how many spots did we move it? So we can count by threes. So we've got 3, 6, 9, 12, 15, 18, 21, 24, 27, right? So we've moved it 27 different places. So we can write this a little bit differently. What we can do is we can say, all right, this would be 5.97 times 10 to the 27th grams. Really what this thing means over here is we've moved the decimal 27 places to the left. And we always want to make sure that it's represented as 10 raised to a power. You can't just have the superscript 27 coming after the 5.97. This is called scientific notation. How many of you have seen scientific notation before? So most people have? Okay, that's good. And we'll be using scientific notation a lot. It just makes it a lot easier not having to write out all of those zeros. All right, we'll do one more. We'll do the mass of hydrogen. All right, and same idea. I'm gonna have to count really quick. I think it's like this. So if we move this all the way after the first non-zero number, I think if I'm counting right, we moved it 27 spots to the right. Let me see, so 3, 6, 9, 12, 15, 18, 21, 24, 20. Oh, I forgot a zero. It's okay. So we moved it all the way after the 27 spots over. All right, so this would be 1.67 times 10 raised to some power. What do you think that number will be? It'll be negative 27 because we're moving it to the right and not to the left. Do you have a question? Or did I miscount? Did I miscount? Shoot. So 3, 6, 9, 12, 15, 18, 21, 24, 25. Oh, you're right. I needed one more zero. But you kind of get the idea. It's very, very tedious writing that many zeros, and like you saw, it's easy to make a mistake. But we moved that decimal 27 spots over, at least I think. I can double check again. And this would be the scientific notation for the mass of one hydrogen atom. Does that make sense? So the thing to remember is if you move a decimal to the left, that superscript number will be positive. If you move it to the right, it will be negative. All right. In addition, we use prefixes a lot too. All right, so I'll show you how prefixes are commonly used. So let's say we have 1 kilogram. This kilo unit is a prefix, right? And if you look on that handout that I just gave you, what's the number associated with kilo? 1,000, right? So it means we're going to multiply this by 1,000, which conversely means that you could write this out as 1 times 1,000, which is just 1,000 grams, right? So we often put in these prefixes to help us. Another way of writing 1,000 would be times 10 to the third. So both of those are completely equivalent to one another. We can use them pretty easily. Let's try a harder one, though. So we'll think about Batman. I don't know if we want to do the Christian Bale Batman or the new Batman. But Batman, we'll say, has a mass of 95,000 grams. So my question for you is, what is his mass in kilograms? What do you think?
95.
Yeah, it'd be 95, right? So if we think about this, we can just remove 3 of those zeros and we could say, all right, 95 kilograms is equal to 95,000 grams. And we know this is true because this kilo unit is the same as multiplying by 1,000. All right? My second question before we head home is, what is his mass in scientific notation? What do you think?
95 times 10 to the third.
Well, let's try that. So 95,000. We know that there's a decimal right there. If you remember, I said when we do scientific notation, we want to move the decimal after the first non-zero number, right? So in this case, I'm going to move this decimal after the 9, not after the 5. That's standard scientific notation. So we moved it 4 spots. So we could say this is 9.5 times 10 to the what? 10 to the 4th grams. So knowing how to use both of these can be really useful. We may interconvert between each of them. All right, hang on to your problems of the day. I'll email Sharon. My guess is she won't want that second problem of the day due until Monday. I'll just kind of fill her in on where we're at in lecture.